All right, hello students. Welcome back to another week of Chemistry of Everyday Life. This week we are on Unit 9 and we are going to focus on a very big topic in chemistry, organic chemistry. How big this is if you were a chemistry major in college, you would spend a whole year at least, your second year, the whole year studying just this topic. So having said that, we're going to condense it all in this 1 hour or so of lecture. So we're just going to go over kind of briefly, so introduce you to some aspects of what is known as organic chemistry, okay? Now, the first off, we want to kind of touch base on what we know from the word organic used in everyday life, right? It's a little bit different from what organic chemists use it as. So for example, you hear of organic produce, organic farming, right? So they're not using synthetic chemicals or like pesticides to grow the food, right? They're using very natural ways of growing the food, and that's what we call as organic, right? And that's tends to be healthier and tends to be better for the environment. So for example, organic farming would not use something like this product that kills weed, which has this molecule called glyphosate. Okay, so this is a weed killer, an herbicide essentially. That would not be used for organic farming. However, here's where it kind of changes a little bit. This actually is an organic compound. Glyphosate is an organic compound according to chemists from the chemistry perspective, because anything that has a carbon in it is technically considered an organic compound, an organic chemistry. Okay, and usually it doesn't just have carbon, it would have hydrogens mostly, and then oxygen, nitrogen, sulfur sometimes also. Okay, so taking a look at glyphosate, we see that it indeed has a carbon or many carbons in it, so therefore it is generally considered as an organic compound. So that's the difference between the definition of our everyday usage of the word organic, whereas in chemistry, it's very specific to saying something that has carbon in it. Okay, so for example, ascorbic acid, vitamin C, is indeed an organic compound. In this molecule represented here, carbons are in the turquoise blue balls. So it has 1, 2, 3, 4, 5, 6 carbons in it. It also has oxygens and hydrogens. Moving on from that small vitamin C compound, we can even be bigger. Like when you think of plastic, it's a polymer, so it's just a unit that repeats itself hundreds of times, maybe. So for example, this is polypropylene. I've only shown a small snippet of it. Of course, again, it just repeats itself in order to make the plastic material that we know. Highlighted in this molecule here are the darker balls here. It's a carbon and hydrogen. So this molecule is basically just carbon and hydrogen, long chains of it. You can get even bigger, right? You can have 6,534 carbons in this one molecule. Okay, what is this molecule? We call this sometimes called a macro molecule. So for big molecule, it's a biochemical molecule. I said here it is an antibody, and it's actually the structure for Keytruda, which is a cancer antibody. It's a drug basically. So in this molecule, it's very big, right? Lots of thousands of carbons, 10,000 hydrogen, almost 2,000 nitrogens, more than 2,000 oxygens, and 46 sulfur. So when it gets to be that big, we don't represent it with these balls anymore, like enzymes and proteins like that. They represent in this kind of a ribbon structure. But we won't talk about that so much in this class. But I show that image just to show you that organic compounds can be very from a couple of atoms only to thousands and 10,000s of atoms. But what they do share in common is that they have a carbon atom, right? At least one. But why are we focusing on carbon? It turns out carbon is quite a unique atom. It has the ability to bond with a lot of other atoms and even bond with itself. And that ability makes it grow, right? Make it, you can, like Legos, you can make it bigger and bigger of a molecule, more complex molecules because of that bonding. And carbon is known as being a tetravalent, meaning it has 4 bonds. Remember how many valence electrons carbons have. It's very unique, right? It's right in the middle of 4, right? It can go, it can lose 4 to gain the octet, or gain 4 electrons to gain the octet too, or rather to duet if it loses 4. So in any case, it's right in the middle. So because it's right in the middle, it loves just to share electrons instead of just giving and taking. So carbons are mainly found as in covalent compounds, as we will see in this unit. Okay, so starting from the simplest carbon compound is because it needs 4 bonds, then it likely will bond with just hydrogens. Right? So 4 hydrogens is the simplest unit seen here. Now, if you replace 1 hydrogen out, and by the way, this is called methane. If you replace 1 hydrogen out and add in 1 carbon there, now you have 2 carbons. See how that 1 carbon is connected to that original carbon, so therefore it has 3 more bonds it needs to make. So therefore it has 3 hydrogens. So this is ethane, and then so on and so forth. You can build it, and then it can be even much longer than this. So this one has 1, 2, 3, 4, 5 carbon chains. So this is called pentane. So notice as when we draw this and the molecule gets more and more complex, we get kind of tired of just drawing all of the atoms in. And we know that there's a pattern for carbon bonding that it always have 4 bonds, whether that be a single bond, double bond, or whatnot, right? It has to have an octet. And it's always surrounded by hydrogens. So we get lazy. We don't want to draw those hydrogens anymore. So we draw what is known as a bond line structure or a skeletal structure, because it's just a skeleton of the atom, of the molecule. So in this, for example, we see there's 5 carbons in here and a bunch of hydrogens. So we draw these lines, and at the end of each segment represents a carbon. Remember, there were 5 carbons, right? So 1, 2, 3, 4, 5. So that's how we draw it, and we just ignore the hydrogens. But we would know, for example, at this carbon, how many hydrogens would you have? Well, we know that there has only 1 connection to this other carbon, so therefore it must have 3 more hydrogens. You see that? So 1, 2, 3. How about this guy here? We know that it's connected to 1 carbon to the left, 1 carbon to the right. So therefore it has how many more bonds it needs to make? It needs to make 2 more to make 4, right? So therefore we know it has 2 hydrogens. See, we see here 1, 2 hydrogens, right? So keep that in mind. And the last thing is that we draw it in a zigzag form, just to mimic the geometry of the actual molecule as much as possible. So it is in zigzag form. So let's go back to this glyphosate molecule we had in the beginning of our discussion. So how would you draw this using the bond line structure? Okay, so it's a little bit different because now we have other things like oxygens and nitrogens and phosphorus, right? So in the bond line structure of this molecule, we keep everything the same, except we have to draw out all of the non-carbon atoms and draw out all the hydrogens are connected to the non-carbon atoms. So for example, this hydrogen here is connected to this oxygen, right? So we have to draw it all out. Whereas these 2 hydrogens are connected to a carbon, which is right here, so we don't draw it out. Okay, so let's trace this molecule. So this OH is there. It's connected to this carbon, which is at the end of this line. And this carbon is doubly connected to an oxygen. So double connecting to oxygen. Then connected to another carbon, which is another just segment. See, this is carbon, so we don't write it in. And the hydrogens, we don't write it in. Then it's connected to a nitrogen, which is connected to a hydrogen, so we do draw it in. You can draw with a line or just write a hydrogen on top. Then it's connected to another carbon with hydrogens, so we don't draw that in. Then it's connected to a bunch of non-carbon atoms, so we do draw all of those in. Okay, so we're going to get a lot of practice with this in our homework this week. Let's go back to the 3 molecules I've shown you previously. Because they only have carbon and hydrogen, we call these molecules, this class of molecules, hydrocarbons, right? Simple enough, right? Hydrogen, carbons. And they are the simplest organic compounds because they only have carbon and hydrogen. Okay. And in this class of hydrocarbons, there are another subclass. One of those subclasses is called alkanes. So basically, alkanes are hydrocarbons. So again, it's C and H, but they only contain single bonds. Okay, so all of these that we show here are called alkanes. Alkanes are often called saturated hydrocarbons. Remember, because carbon can only have 4 bonds. So this carbon, for example, can only have 4 bonds, and it's connected to 1 carbon already. So it can have 3 more bonds. So we fill all those 3 bonds with hydrogen. We saturate that carbon with the most amount of hydrogens possible. That's why we call it, that's why we call these kind of hydrocarbons saturated hydrocarbons, right? So for example, this carbon here is bonded to 2 carbons, and so it has only 2 more bonds. So we saturate them with hydrogens. Whereas this carbon here has only 1 bond connection, so it has 3 more places to have hydrogen, so we saturate it with hydrogens. So anytime it's just a single bond in your molecule, that hydrocarbon will also automatically be called saturated hydrocarbons. And they do not mix well with water. And can you remember why that is from a previous unit? So if you only have carbon-carbon bonds, meaning they are the same, so they're nonpolar, and carbon-hydrogen bonds, again, the difference in electronegativity between a carbon and hydrogen is 0.4, which is considered a cutoff of being nonpolar. So if you only have nonpolar bonds in your molecule, the entire molecule is considered nonpolar. And remember that principle of like dissolves like. So water is polar, and alkanes are nonpolar. Therefore, they do not mix well. You can probably see this in the news, for example, when there's an oil spill, right? So all of those oil is a nonpolar compounds, various nonpolar compounds in there, and water is polar, right? So you don't see the oil just dissolving into the water, into the lake, into the ocean, for example. You just see it kind of separated on top, and the water on the bottom, right? So they don't mix well. And you can also see this as an example when we talk about a heterogeneous mixture of a salad dressing when you mix oil and vinegar, right? Vinegar is basically aqueous, meaning it's dissolved in water, whereas oil is just oil, so they don't mix very well. And just to go back to that point too, hydrocarbons tend to have lower density also. So that's why when you see an oil spill, they kind of the oil stays on top, the water is on the bottom. And they are not very reactive. They are not very reactive, so we don't really learn that much chemistry from them, except for one important thing. They are quite combustible. So they burn very well. And because they burn very well, that makes them actually very important in our economy, right? So that's basically the gasoline that we have, because they burn very well, giving us the heat and therefore the energy. Here's a list of the 10 alkanes that we have. And we can learn how to name them based on the number of carbons they have. So let's go over these names. The first one is methane, when it has only 1 carbon. The second one is ethane, when it has 2 carbons. The third one is propane, when it has 3. 4 is butane. So all those first 4 is harder because there's no real system to remember them. So just kind of make flashcards to remember those names. And you are required to know the name of the first 10 alkanes. Now, going on from 5 and above, it gets a little bit easier because it has those root words that we know, like a pentagon is a 5-shaped or 5-sided shape, right? So a 5 carbon is known as pentane. 6 is hexane. 7 is heptane. 8 is octane. 9 is nonane, and 10 is decane. I think, did we talk about this before? If not, I'll just mention it again, why these root words, prefixes don't make much sense, right? For example, I mean, they do make sense, but in another sense, they don't. For example, here, we have octane, right? Oct is 8, right? So why is October not the 8th month? October is the 10th month, right? Or nonane, which is like 9 or like November, right? So November is not the 9th month, it's the 11th month. Or December, like that cane here is not the 10th month, it's the 12th month. Why is that? All right. So it used to be because there were only 10 months, right? And then I think during the Roman times, the Gregorian calendar added 2 more months. And where would they want to add these 2 more months? Well, the king wanted to name these 2 months after themselves. And where would you want your month, your named month, to be? Would you want to be at the end, like in the winter, or somewhere nice in the summer, right? So they squeeze themselves into the summer months and then push every month back. So that's why Julius Caesar got July and King Augustus got August, right? Or St. Augustine got August. So that's why July is 7, August is 8, and then September used to be the 7th month because sept means 7. Now is the 9th month. And October, oct, used to be the 8th month, plus 2 is now the 10th month, and so forth. Right, so that's how you could remember these names a little bit better by knowing the prefixes. Okay, and listed over here, you can see I want to introduce you to this kind of nomenclature here, or this kind of writing here. It's called the condensed structural formula. So in a condensed structural formula, all the CH bonds are omitted. So any hydrogen and carbon bonds, you just kind of clump them together. So this carbon here would have, remember the ethane we saw earlier with, right? This is the ethane molecule. It would have this carbon with 3 hydrogen bonds and this carbon with 3 more CH bonds. So we clump all of these together as, so we write CH3, and this one is CH3. What about this guy here? This carbon has 2 hydrogens only, so we will write this as CH2. So CH3, CH2, 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 CH3, right? So that's what a condensed formula is. It condenses it down to we don't write the carbon hydrogen bonds anymore. So we cluster them in these clusters of carbons, and then how many hydrogens are attached to them. Another way sometimes people write it is that all of the bonds are omitted, and we just see clusters of atoms. So we just omit all of these bonds too. So we just assume, of course, they're connected, right? We assume that the carbon are connected. So we just write CH3, CH2, 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 CH3. So that's an even more condensed form of that formula. And the most condensed form you can have is just the molecular formula, which isn't very helpful because it doesn't tell you how things are connected, just how many atoms there are in that molecule. Okay, so now that we have knowledge of all of these longer chains of alkanes, of carbons, let's talk about some concept known as isomers. Remember the root word iso? When we talk about isotopes, it's very similar. Iso, pun there. Iso means same, right? Like an isosceles triangle means they have the same length, at least 2 sides are the same. So iso means same. So isomers are 2 molecules that somehow are the same in some ways. Okay, they are compounds with the same molecular formula, right? So it tells you how many atoms and that molecule has. They have the same amount of atoms basically, but they're different. But they differ in structural formula, as in their connectivity is different. So for example, the butane that we saw earlier has 4 carbons in a straight line like this. And because it is on a straight line like this, we can also call it with a N in front to represent that it's just a linear chain. But we can also rearrange the last carbon and not connect it to the 3rd carbon, but connect it to the 2nd carbon instead, right? And we get this molecule. Notice that it has the same amount of carbons and the same amount of hydrogens, right? But it's actually a different molecule. It has different physical properties. It has different boiling points and melting points, for example. And so we would, because it acts and behaves differently, we have to say it is a different molecule and give it a different name. So for example, we would call this 2-methylpropane. In this class, I won't make you name a complicated alkanes, but I'm just saying it for you to know about it. And it's called 2-methylpropane because the long chain up here is a propane, and on the 2nd of that carbon, we have this 1 carbon group coming out, and 1 carbon is methane, right? So we call it 2-methyl. 2 meaning it's on the 2nd carbon. Again, I'm not going to make you know how to name that in this class. So that's isomers. Okay. Now let's take a step back and talk about these highlight some of these alkanes and their physical properties and see what kind of patterns arises here. So we see here methane, the lowest one, with only one carbon, is actually, you actually know this one, right? If you have a gas stove at home, like if you have an electric stove, you may not know it, but it's the gas when you turn on your stove to cook or your oven to cook. That is the gas that's coming out. It's a natural gas. It burns. Uh, so at room temperature, that's what this means here. At standard temperature and pressure. So standard temperature is room temperature. Pressure is just atmospheric pressure. It exists as a gas. Right. So we see that when you turn it on, gas leaks out. Do you notice that if you leave it on, you can smell an odor, right? And remember we said this class of molecules is quite combustible, so it burns, so it's quite dangerous if you just let it if you have a gas leak. But it turns out this gas doesn't have any odor, right? So if there's a gas leak, you wouldn't know it. That's dangerous. So the government actually puts in, or the companies actually put in a thiol molecule that has that bad odor, so that we can sense it if we have a gas leak. So indeed, methane is odorless. It's just spiked with a molecule that's inert, but it has a smell. Okay, let's move on to now having 3 carbons. When you're at 3 carbons, you're propane. And this is the kind of the gas you buy at the gas station. You know, you like for barbecue, you have this gas tank and you kind of fill it up at the gas station. That's propane, right? It's also a gas. That's why you have to hold it in a kind of that container, pressurized container. It's also, yeah. And then the next one is butane with 4 carbons. Again, it's still a gas. Then once you move on beyond that, and particularly one example is octane, you become a liquid. Right? Octane, we know, is the gasoline component. And actually gasoline component is a mixture of octanes, of alkanes that are composed of 5 carbons to 12 carbons. So octane is one of them, which is 8 carbons, right? Okay. And then if you move even further down the list, for example, when you have 18 carbons, you are now wax, very waxy. You are a solid. Okay, so like other kind of high carbons would be things that exist in petroleum jelly, right? All your lotions and stuff will have really high carbon chains. So notice that as you increase the amount of carbons you have here, you will increase what is known as intermolecular force. All right, because you're increasing this intermolecular force. They stick together even more. Because they stick together even more, they are at room temperature either solid, but if they stick a lot, if they stick around a little bit, they are a liquid, and they don't have that attraction. They're just don't stick together. They just float away from each other. They are a gas. Okay, so that's one trend we want to take a note at, is that intermolecular force in alkanes. We talked about how alkanes can be in a linear fashion. They can actually fold and link up to become a ring onto themselves. And we call this cyclic hydrocarbons. But the rules stay the same, right? So a carbon needs to have 4 bonds. Well, this carbon here has 1, 2 bonds to carbons. So therefore it has 2 more bonds. So those are hydrogens. So that rule still stays the same. So not much change when they are cyclic. To name them, we just add the word cyclo in front. So for example, if this is a 3-carbon, what do we call that? Propane, right? So, but now they're stuck together. So they are cyclopropane. Okay, what about this one? 6 carbons, what do we call that? Hexane, right? So we call this cyclohexane. Notice when we draw the skeletal structure of it, remember we don't draw in carbons and hydrogens, so it's just like a hexagon shape. And this is a triangle shape. All right. Now we talked about how linear hydrogens having the most amount of hydrogens possible on them, and we call that saturated, right? And in fact, when you are a ring, you lose 1 pair of hydrogens, or you lose 2 hydrogens as a compare, like cyclohexane compared to linear hexane. That's because, you know, remember if this bond was broken, it would be a long chain, right? A linear chain. And at the end of each chain, it would be CH3 and CH3. Well, if you are linked together, you have to get rid of one hydrogen in order to have that one extra, the fourth bond, right? So alkanes have two less hydrogens than linear alkanes of the same number of carbons. Speaking of less number of hydrogens, let's go to unsaturated hydrocarbons. Okay, so the opposite. Saturated means you have the most amount of hydrogens possible. Unsaturated means not most possible. So for example, remember when we have two carbons, how many hydrogens would that molecule have? If you go back to your notes back there, you would see it would have 6 hydrogens, right? So 3 hydrogens for each carbon. Well, what happens when the two carbons are doubly bonded? If they are doubly bonded, they share 4 electrons with each other. So they only need 2 more bonds to make the octet, right? 4 here, 2 here, and 2 here makes the octet. So instead of 3 hydrogens, it bonds with only 2 hydrogens. So therefore, it's not the most hydrogens possible. So that's why we call it unsaturated. So this term you will actually know in everyday life when we talk about saturated and unsaturated fat. It's the same definition. Okay, but to step back a little bit, when hydrocarbons are unsaturated like that with a double bond, we give it a different class. It's a different class or family of molecules. Instead of alkanes, we call them alkenes with the E replacing the A. So, and the name of these things just replaces the A to become the E also. For example, if this was ethane, if this was a single bond, because now it's a double bond, we call it ethene. That's the kind of systematic way of naming it. But chemists also have a kind of a familiar way, a common way of naming it that's not systematic. So this one can also be called ethylene, but the ene is still in there to let you know that it is a double bond. So what is ethylene? Well, it's basically we don't see it much, but it is the precursor or the ingredient to making plastics like this. Okay, so like I said, I alluded to this earlier about being saturated, unsaturated. It's the same definition as in saturated fatty acid versus unsaturated fatty acids, right? If it's saturated, it is full of hydrogens, right? So this is a fatty acid. It's basically the alkane chain, but at the end of it, it has this other modality. We'll talk about this in a bit. This carbon, oxygen, hydrogen modality. All right. So that's saturated, fully saturated. And then, however, there are instances where a carbon-carbon bond is becoming a double bond instead. Okay, so because of that double bond, you're losing 2 hydrogens. So you are now unsaturated fat. Okay, so that's the difference between these 2 fats. And what do we know about saturated fat? They are actually healthier for us, right? They give us good cholesterol, for example, whereas unsaturated fatty acids, oh, I'm sorry, the opposite. Unsaturated fatty acids are the healthy fat, good cholesterol, and the saturated fatty acids are the unhealthy, the bad cholesterol, as they say. I was reminded because you see olive oil, yeah, avocado, good, fish, good, nuts, good, you know, meat, dairy, you know, not good fat. Okay, now all of these these fats are actually natural, and they occur in nature as seen here with all these pictures of the examples where they are found. There's another type of fat, and this brings us to another idea. This is also connected to the idea of isomers. So there's something called cis and trans, and if something is a cis, it is an isomer of the trans, meaning they are the same. Everything in there about them is the same, except the way they are oriented in 3-dimensional shape or 3-dimensional space is opposite of each other. Cis means on the same side, trans mean on the opposite side, like the transatlantic railroad, right? It goes from one side to the other side, the Pacific to the Atlantic. Trans means going across. Cis, then therefore, is the same, meaning the same. Okay, so when you have a double bond, notice that in the single bond, notice that in a single bond here, it is just know that a single bond is free to rotate. So this molecule can rotate around. So if this hydrogen is facing you right now, it can, if this single bond here can rotate, this hydrogen can be facing opposite of you, away from you. Whereas in a double bond, there's this bond, because it's doubly bonded, it cannot rotate anymore. Okay, now I have very different colors. So let's have a blue ball here and a red ball here, right? So they are in the same phase with each other, but this is a single bond. That means it's free to rotate. See how the red now is far away from the blue? So we can call that quote unquote trans, right? So that's in a single bond. Now what happens when it's a double bond? Okay, I'm gonna remove one atom from each carbon and make a double bond. There we go. So this double bond here, see that double bond? It has two bonds connecting to the carbon in the center. I can't rotate this. It's basically stuck. Okay, so this blue ball and this red ball is permanently facing far away from each other. So because of that, this is called a trans isomer of this molecule. See that? Because it is permanently stuck like this, if you made another molecule that was the opposite, where these two colorful balls, red and blue, are on the same face and closer to each other, it is now called a cis isomer. Because it is stuck in this position, these two molecules are actually very different from one another. Okay, so these isomers are very different, but so they will behave differently. They will have different chemical properties, different biochemical properties. Okay, so that's cis and trans. So how does that relate to fats that you hear? Have you heard of cis fat and trans fat? Maybe trans fat, right? Okay, so there are those two kinds of fat. Okay, so it turns out that the fat that we are found naturally is known as this, as a cis double bond. So that's called the cis fat. And so it looks like this with a little V-shaped kink in it. The other one is called a trans fat. So the hydrogens are on opposite side. Because of that, this molecule tends to be straighter. Okay, so going back to this structure over here, remember we said the unsaturated fat is the good fat and the saturated fat is the bad fat. And then this new fat that we found here, the trans fat, is also unsaturated, right? But what? Is it good or bad? You always are told to avoid trans fat, right? So trans fat is actually bad for us. So it is very similar to saturated fat, even though it is unsaturated. Why is that? Can you see why that is? Notice it's very straight, right? This has a kink in it. This also is very straight because of that trans geometry there. Because of that, it behaves very much like saturated fat in being very dense, because it's kind of it's linear, so it can stack upon one another very nicely and pack it up, very dense, so that's bad. Whereas the cis fat has a kink in it, so it doesn't pack very nicely in your body, in your bio and in your lipid bilayer in your cells. And then you can research onto why that's not good. Quickly, one reason why cis fat is better is because of that kink. So molecules, signals can go in and out of your cell more easily, whereas this one blocks everything because they're so densely packed because of that linear nature they have. Okay, so now you know the difference between cis fats and trans fat. Oh, one more thing about the trans fat, it's not found in nature. That's another reason why they're bad for us. This is made in the laboratory. So because it's not found in nature, your body doesn't really know how to process it. So that's why it's another reason why it's not. People tell you always to avoid trans fat. It's not natural. Okay, so that was the first type of unsaturated hydrocarbons. There's another one called alkynes. So this time, instead of having two bonds, we have three bonds. So a triple bond. Because as a triple bond, now that carbon only has one more bond left, so one more hydrogen. That's why it's unsaturated. And to name them, we just change it from the A to a Y now. So like this is an ethane before, And when it's a double bond, it becomes ethene. Now with a triple bond, it becomes ethyne. And where do we use this? The most common alkyne you will know is acetylene, or also known as ethyne, is as a gas, and it's used to in welding. Basically, when it burns, it's very hot, and so it's used to weld things. All right, next class of molecule are also hydrocarbons. It's a very unique one, and we call them the benzene ring. Okay, so anytime you have 6 carbons and 6 hydrogens, and they have double bonds in alternating patterns like this, we call that benzene. Now, it turns out that that double bond can be represented like this or like this. Notice that you can alternate them. This one was double, it's no longer double. This one is single, now it's double, right? So which one is it really? It turns out both of these representations are not accurate. It has to be a merge between them. It has to be a hybrid of them. So that's why this molecule is quite special. It's not a double bond per se, but the double bond is throughout, and it's shared in all of the carbon-carbon bonds. So because of that, you can also sometimes see it drawn as a circle instead of just alternating double bonds. So benzene is the name of this molecule, and it's a solvent. We use it as a solvent. It's quite carcinogenic, so it's not used that much in everyday products anymore, but it's still used in the lab. But if that benzene ring is part of a molecule, it's totally different. For example, if it's part of this molecule here, it just is the molecule fentanyl, which is it's for pain relief, but it's an opioid, so people tend to abuse it, and it's not. It could be lethal, right? You've heard about fentanyl overdose raging across America, right? So that's what that is. So this brings us to our introduction of something called a functional group, because there are millions, tens of millions of organic molecules. We can't study each one of them. So we study them in kind of their family. So to see what kind of similar reactivity they have. So this family is called this is the first family we'll talk about. It's called the aromatic family. Okay, so in this family, as long as we have the benzene ring, it is known as aromatic. Now, the name is kind of a misnomer, because in the beginning of the discovery of these compounds, they tend to be very aromatic. They smell good. So that's why they're called the aromatic compounds. But it turns out lots of molecules with this structure doesn't have smell or doesn't smell good at all. But the name stuck. So there we go. So as long as it has that benzene ring or have properties similar to those benzene rings, it's called an aromatic compound. So for example, here we have toluene and xylene. So it just has different substitutions of carbons coming out of it. And basically these molecules are found in your gasoline or as solvents in the lab. Naphthalene, you might know, it's a mothball. So it's good to kill the moths. So it has that unique odor that you might have smelled. Okay, so that brings us to our last part of this lecture, are talking about the functional groups. So we talked about all those carbon hydrogens before. Again, we said they weren't very useful. They weren't very reactive. We can't really do much with them except burn them, which is great, but that's all we can do with them. But there are when you start incorporating oxygens and nitrogens and sulfur into a molecule, you have families of molecules that behave in the same way. So we call this functional groups. Okay, so in your textbook, it lists out most of the functional groups, not all of them, and how they're named. So for example, alkane is not a functional group, so we skip that. We actually talked about alkene and alkyne already, and how they are named. So those are also functional groups. And now the remainder of the lecture, we talk about these other functional groups that has other atoms in them, other than carbon and hydrogen alone. So we have here alcohol, which is the general formula is ROH. R represents just any alkyl chain. Alkyl meaning alkane, right? So as long as any carbon hydrogen chain, but connected to a OH, we call that an alcohol. And we name them with a name ending of OL. Anything with a thiol it's just very similar to an alcohol, but instead of an oxygen, we have a sulfur. I won't talk about this one so much, other than right now. So yeah, that's a thiol. And one thiol I mentioned earlier was they spike your gas stove with a thiol compound that stinks or has an odor, so you can detect it. So that was a thiol example. Another one with an oxygen in it is called the ether. It's basically one oxygen with two alkyl chains on the sides. And then we go into this class of carbonyl carbons. Carbonyl meaning carbon, oxygen double bond. You see they have all of that. But just how they're different is what's connected to the carbon. So if it's an alkane versus and a hydrogen on the other side, we call that an aldehyde ending in al. If they're both alkane chains, we call that a ketone, and we end the name in one. If on one side it has an OH instead, and we call that a carboxylic acid, and it ends in oic acid. Okay, so we'll go about these in detail in the following slides. So our first one is the alcohols. So they contain this group called OH, called hydroxyl group. So that's the name for that OH. But if it has a hydroxyl group, the compound isn't considered an alcohol. But sometimes we can also call it an alcohol functional group or a hydroxyl functional group. They're kind of interchangeable. What is the most famous alcohol we know of? Right, the thing you're gonna party with? No, okay. If you are of age, you may drink alcohol. It's so pervasive, we just call it alcohol, right? But in actually, the compound that is the main ingredient in what we know as alcohol is ethanol. Remember, eth meaning two carbons, right? So ethanol has two carbons with the OH at the end, and that's what makes that gives you a buzz. So how is ethanol made? Traditionally, right, from thousands of years ago, cultures have been making alcohol with grains of some sort, or even basically you need the sugar from the grain. So even you can just use the sugar here. We add some yeast in there, so it has some biochemistry going on there, and then the product will yield this ethanol molecule along with carbon dioxide. That's why it bubbles out. That's the gas. Okay. But there's another way to making ethanol is industrially in a laboratory, in a factory. We can use ethene. Remember that we saw that alkene earlier. If we react it with acidic hydrogen, with acidic water a little bit, it will also create that ethanol. And so this ethanol is not good for consumption. But we can use it to in the lab, or we can use it to burn things, right? So it's not good for human consumption, basically, or it's not deemed to be good. So to prevent, but essentially it is the same molecule, right? Because it is the same molecule, it is both healthy, or it is both safe, quote unquote, safe for us to drink. But the government doesn't want you to drink this. So because this ethanol, where you can drink, there's a tax for that, right? Where this ethanol, there's no tax. Where this other we call it synthetic, maybe ethanol, because it's made in the lab. The government doesn't tax for that, so they don't want you to just buy this and drink it and don't get taxed for it. So instead, when they make this, they have to put in they spike in another compound that makes us nauseous, so we don't drink it. And so that compound, and so that kind of alcohol is called denatured alcohol. So if you hear that denatured alcohol, do not drink it. It is not. It's gonna make you sick. Okay, they add a compound to make you sick because it's not meant to be drink. You can also find ethanol not only in your alcohol, but you can find it when you go to the gas pump, right? So ethanol has that carbon-carbon bond, so it can burn nicely also. So it is used in your gasoline sometimes. And the government subsidizes because we make so much corn in America. That corn can be fermented into alcohol, and so they subsidize farmers to grow corn to make us this fuel for our gasoline. Another common alcohol that you may encounter every day is isopropanol, or with its more common name, rubbing alcohol, right? So that's the disinfectant in your um, in your um, in your disinfectant. And it is a 3-carbon chain with an alcohol right in the middle. That's why it's prop, because it's three carbons for propane, right? Propanol. It's called iso because there are different isomers of propanol. The OH could be at the end here, right? That could be different, or it could be here. So this is the one that's mostly used. Now let's talk about alcohol as a functional group, not just as, the main thing, like in ethanol and isopropanol. It's very, 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 very common to find alcohol functional groups, hydroxyl groups in natural products. Like in glycerol, which is the main ingredient in your petroleum jelly, your Vaseline, right? Which is, used to hydrate your skin. It has more than one OH groups, more than one hydroxyl groups, 3 in fact. So each carbon basically has a hydroxyl group. You can also see in an ethylene glycol. Now, that was 3 carbons. This is only 2 carbons, and both carbons will have this OH group. All right, this is seen as your main ingredient in your antifreeze. It turns out, though, this is funky, that this ingredient, this ethylene glycol is kind of sweet. So that's why they have to put a warning here that it's harmful or even fatal if swallowed. I've heard scary stories about how this antifreeze could leak down from your car, and maybe like your pet, like a dog, could lick it up because it's so sweet they like to eat it, but it is basically a poison. So that's the alcohol there. And then if you zoom out into even more natural products, and I can't list them all, but here's one example: is cholesterol itself, the molecule. Again, that's just a molecule important for biosynthesis of vitamin D. It's important in synthesis of hormones also, I guess. So that's the alcohol group right there you see at the end. Yeah, I highlight there in red. The whole molecule is quite complicated, and then there's an alcohol group there. Okay. Now let's move on to ethers. Ethers are very similar because it has an oxygen, but instead of having a carbon on one side and a hydrogen on one side, it has carbons on both sides. We can represent it as ROR or ROR prime. The R prime just means that it is a different R, different alkane, right? So for example, this on both sides is the same, right? So the R are the same. So we can say this is ROR. So this is called diethyl ether. 2 ethane chains connected to the same oxygen. But the R's could be different. So ROR prime, for example, this R is quite different from this R, right? You can see this R is like connected to this benzene ring. This R is just single bonds all over. So that's why the prime is there. So this is a vitamin E, an antioxidant. You can see it has an ether moiety in there. Morphine. Ooh, look at this structure here. Fancy. Morphine is opiate used for relieving severe pain, or it could also be misused and abused. It also has an oxygen combined with 2 carbons on the side, so that's an ether moiety, ether functional group. The most produced ether, however, is this ethylene oxide. And the reason for that is because it is used in a reaction, acidic water, to create ethylene glycol, the antifreeze we talked about earlier, right? So this ether is also a cyclic compound. Now, let's talk about a big class of functional groups. All of these functional groups have this same pattern. It has a carbon-oxygen double bond, and we call that a carbonyl. A carbonyl. So when you're a carbonyl with connection to a hydrogen, we call that an aldehyde. When you're a carbonyl that's connected to just carbons, we call that ketone. When you're a carbonyl that's connected to an OH, hydroxyl group, we call that carboxylic acid. Instead of an OH, it's an O alkane, OR, call that an ester. Instead of that ester, we replace that with a nitrogen instead. We call that an amide or amide. Okay, so we'll go over all of these one at a time. So our first one is aldehyde. Ooh, aldehyde. Formaldehyde is the simplest of the aldehydes. It just has two hydrogens on the sides. It's used in as a preservative in funeral homes. Right? You pump your dead body, pump the corpse with formaldehyde to kind of like freeze everything in place so it doesn't decompose. It will eventually, but for a while it stays the same until that formaldehyde is gone, I guess. But if you put like a brain or any kind of a biological species or specimen in a jar of formaldehyde, it will stay like that. Okay, so that's formaldehyde. Another aldehyde you know is benzaldehyde. This is the odor that they put in food to make it smell like almond. Benzaldehyde. So you notice that has a carbonyl that's connected to one hydrogen. As long as it's connected to one hydrogen from that carbon of the carbonyl, it is an aldehyde. Next is the ketone. And we know this in this molecule here in acetone, which is nail polish remover, because it has a carbonyl with two carbons connected to that carbon of the carbonyl. Another one is they are super prevalent in natural products. For example, here progesterone, right? That's the hormone that pregnant people exude in order to sustain a pregnancy, right? So that's called progesterone. See that carbonyl, that ketone is here and here. On the flip side, it is also in testosterone. These are all steroids, are hormones. They're very similar to each other, yet very different. Testosterone is the hormones that make the male build muscles, right? And beyond, and other stuff. It could affect your brain, etc. That's testosterone. It also has the ketone moiety. One way you may have heard of ketones is that when you go on a particular diet, you release a lot of these molecules when you pee out. The keto diet, right? That's because it has a lot of ketones as a byproduct in that biological processes that happen in your body to process the when it digests the food in a certain way that when you don't eat carbs, right? Yeah, so that's a keto diet because of the ketones that is released. Next is carboxylic acid. Okay, so we've seen carboxylic acid before when we talk about that. When we talk about the acid part in a previous unit. Acetic acid here is our common one. It is the main ingredient in vinegar. As long as you have the carbonyl with connection to a hydroxyl group, that's called carboxylic acid. This one is called butyric acid, and it's responsible for smelly socks. Okay, and so if you have smelly socks, you have a lot of butyric acid, and basically body odor is it smells like it's rancid, like smell. That's butyric acid. When the acid though, because remember acid means it could be removed, the proton can be given off. That's what makes it an acid. If you remove that proton, it's going to be a negative charge. Remember, protons are positive, so this leftover is positive. Negative, I mean. The leftover is negative because the proton is positive. So if you remove that, then you have to balance it with something else. Balance it with a metal, right? A cation. So in here, when you remove that part, you have to balance it with a sodium. But and so technically this is benzoic acid, but if you remove that acidic part and you add in the metal, this is called sodium benzoate. So I want to just include that in here, even though it's technically not an acid anymore, right? Because it's just a salt. Its precursor was benzoic acid. Anyways, so sodium benzoate is what you are very familiar with, maybe. It is found everywhere. It is used as a food preservative. If you look at any of your, maybe today, go look in your pantry, it may not appear in every single item, but look in your items to see if there has any sodium benzoate in there as a food preservative. All right, moving on to esters. Remember, esters are just compounds with carbonyl connected now with an oxygen and an alkane at the end. Not just oxygen and hydrogen, but oxygen and an alkane. So we call that an ester. Esters are super fragrant, right? So most of the simple molecules of esters have a particular fragrance to them. So for example, pentyl acetate is the molecule responsible for the fragrance of bananas. And then here we have, and there's a lot, so you can search this up. If it's pentyl butyrate, it has the smell of apricots. And if it's benzoyl acetate, it has the smell of jasmine. Now, if this ester is in a bigger compound, it doesn't have this kind of distinct smell anymore. But if it's in small compounds like this, it will have that distinct smell. Amides. Okay, so for amide, it's the same thing. We have a carbonyl, but instead of being connected to a carbon, oxygen is connected to a nitrogen instead. So if it's connected to a nitrogen, we call that an amide or amide. So this is an example here is Tylenol. And then nylon is a polymer, meaning it repeats itself. This structure just repeats itself. But regardless, it does have a amide functional group in it. And nylon, as you know, is the synthetic fiber that's like silk. Not natural, synthetic, because it's a polymer. Speaking of things with nitrogen in it, let's make a pivot away from carbonyls to talk about amines. Amines are basically atoms with a nitrogen and single bonds and not connected to a carbonyl, right? So if it's a carbonyl, a connection there, then it's an amide, but if without, then it's an amine. Like ammonia is the simplest one, NH3, that's your simplest amine. But here we can see it even more so. We see this nitrogen connected in 3 different ways to carbons, and in this molecule known as morphine, again, lots of molecules will have this, and they are here. For example, here, this is adrenaline, right? That's the fight or flight hormone. And then we have here noradrenaline. By the way, discussed in chapter 7, this is not the same textbook, so ignore that. This is noradrenaline, right? So this is now a drug. It regulates heart rate and dilates your air passages here. It's a drug. And then we have here dopamine. This is also a drug, but also natural in your body. Regulates motor skills and emotions. I think they give this to help with Parkinson's. Dopamine is basically the also the molecule that is released when you are super happy, maybe after an exercise. Dopamine. Okay, so nitrogens made with just single bonds, then it's amine. That wraps up our discussion of organic chemistry this week, talking a lot about how organic compounds is just defined with a carbon, and talk about skeletal structures from that, isomers, and then ending our lecture today with function groups. So you should be able to identify function groups if I give you a structure. And then if I give you a structure, you should be able to know that how many hydrogens are not drawn in, because it's assumed. So study a little bit about skeletal structures. So this is a gateway to let us understand 95% of the molecules known to humanity, right? So this chapter is quite useful.